Hello and welcome back. In this lecture, we are going to continue our discussion on quadratic equations, and let's continue with question 41. Find the values for a, the parameter a, such that equations x plus y equals 2a and xy equals 9 have real solutions. Again, so x and y are unknowns, right? And what we are given is the sum of the two unknowns and the product, and we know that if we have the sum of product of two numbers, we can write down a quadratic equation for them. So assume that z is our variable, the equation variable. So we know that the quadratic equation is z squared minus sz plus p equals 0, sum and product, right? So therefore our equation is z squared minus 2az plus 9 equals 0. And because we have a factor of 2 in the coefficient of z, I'm going to use delta prime, which is minus a squared minus 9, a squared minus 9. And if we want to have real solutions, it could be two distinct real solutions or two identical solutions. Delta prime must be greater than or equal to 0. Therefore, the absolute value of a must be greater than or equal to 3. So this implies that either a is greater than or equal to 3 or a is less than or equal to negative 3. We will get back to these inequalities with the absolute value function later on. But for now, we know that either a is positive or negative. Therefore, either a is greater than or equal to 3 or the other way. So we can choose number 3, a greater than or equal to 3. Alright, so the second property here is that determining two numbers with given sum and product of them. Just exactly like the question 41 that we discussed. So we have the sum, s, and the product, p, okay? And then what happens is that the quadratic equation is x squared minus sum times x plus p equals 0, okay? And if our two roots, let's call them x1 and x2, then this quadratic form x squared minus sx plus p is actually, if you factor it based on the roots, you end up with x minus x1 times x minus x2. And this is a general way of factorizing any polynomial, not just quadratic. You can always factorize it based on the roots of the polynomial. Question 42. The product of two numbers is 1, minus 1, therefore p is minus 1. And the sum is 4, therefore s is 4. What is the ratio between the bigger number and the smaller number? Okay, so we form our quadratic equation, x squared minus 4x plus minus 1 is equal to 0, okay? And the ratio, so we are looking for x1 over x2, and this ratio should be greater than 1 because we're assuming that x1 is greater than x2. We're looking for the ratio between the bigger number and the smaller number. And alright, I can solve this. I can use the delta prime for, but I'm going to use just simple, make it a complete square. X minus 2 squared is equal 4 plus 1 is 5. Therefore, x is 2 plus negative square root of 5. So we have two roots. x1 is 2 plus square root of 5. Obviously, this is the larger root. And x2 is 2 minus square root of 5. Therefore, the ratio x1 over x2 is 2 plus square root of 5, 2 minus square root of 5. But you don't see it in the choices. The reason is that we have to go one step further and make the denominator a rational number by multiplying both the numerator and denominator by 2 plus square root of 5. And in the denominator we get 4 minus 5, and in the numerator we get 4 plus 5 plus 4 square root of 5. Okay, so eventually the ratio that we are looking for is minus 9 plus 4 square root of 5, which is the second choice. Right, the third property, computing the symmetric expressions of roots. So what is a symmetric expression? A symmetric algebraic expression is an expression when you interchange the position or the position of the variables is remains the same. For example, x squared plus y squared. If I interchange the position of x and y, I get y squared plus x squared, which is still the same, right? So this is a symmetric expression. Or x cubed plus y cubed plus 3xy. So if I interchange the position of x and y, instead of x I write y, instead of y I write x, I get y cubed plus x cubed plus 3yx. This is still the same, right? And most of these expressions, especially if they're algebraic or in terms of polynomials, you can always write them as a function of sum and the product of the roots. It's always possible. And I have some examples here which we're going to look at. So x1 squared plus x2 squared, and these are the roots. x1 and x2 are the roots of a quadratic equation. And this is a symmetric expression, so I can interchange the x and y and the expression still remains the same. And I can use the identity of a plus b squared, so this becomes s squared minus 2p. x1 cubed plus x2 cubed. Remember, I can write this down. Remember this identity, x plus b cubed is a cubed plus b cubed plus 3ab, a plus b, right? Therefore, x1 cubed. So if we are given this one, x1 cubed plus x2 cubed is x1 plus x2 cubed, which is s cubed minus 3 times the product of the root p and times s. So s cubed minus 3 sp. And the fourth power, x1 to the fourth and x2 raised to the fourth. Still, this is a symmetric expression, so, and it's algebraic, it's a polynomial. So I should be able to write it down in terms of s and p, sum and product. And the way we're going to do this is we do a change of variables. So x1 squared, let's say, is x capital X, and x2 squared is capital X2. Therefore, we end up with x1 squared capital plus x2 capital squared, which we already know, x1 plus x2 squared minus 2 x1 x2, which is this little one's square. But then this one is already in the first item that we discussed, right? Capital x1 is x1, so this becomes s2 minus 2p. So we end up with s2 minus 2p squared minus 2p squared, okay? Now there are other expressions that are not. So the first three terms are polynomials. These ones are rationals. So rationals are basically have numerators and denominators, but the numerators and denominators are all polynomials, okay? So these are symmetric expressions. So if I exchange the position of x1 and x2, the expression remains the same. So I should be able to write it down in terms of s and p. So for example, the first number 4, 1 over x1 plus 1 over x2. We know how to sum the rational numbers. So the product of the denominators and divided by the first denominator, x2 comes up, and the second denominator, x1, comes up, which is s over p. Again, the same thing here. 1 over x1 cubed plus 1 over x2 cubed is x1 x2 cubed. We end up with x2 cubed plus x1 cubed. And you see what happens here. The product goes in the denominator, but then we end up with a polynomial that we already know. So s cubed minus 3sp divided by p cubed. Sorry, this one has to be p cubed here. And the difference. So the number 7 is interesting. The difference, we already talked about it in terms of delta. If you remember, we said that the x1 minus x2 is delta over a, right? But you can also write it down in terms of s and p. The way you do it, you square it. D squared is x1 squared plus x2 squared minus 2x1 x2, right? And we already know that x1 squared plus x2 squared is s squared minus 2p, and then we have minus 2x1 x2, another 2p, so s squared minus 4p, right? Therefore d, the magnitude or absolute value of d, or absolute value of x1 minus x2, is a square root of s squared minus 4p. Okay. Question 43. If x1 and x2 are roots of x squared minus 4x plus 1 equals 0, then what is square root of x1 minus square root of x2? Okay, let's call this d, the absolute value of square root of x1 minus square root of x2. And again, this seems to be a symmetric expression. If I exchange the position of x1 and x2, the result is not changing. And if I square it, I square the first term, x1, square the second term, x2, minus twice square of x1 and x2. Now we see here, we're assuming that the two roots are positive. Okay. And even if they're not positive, we can still solve it. We go into complex numbers, but the result should stay the same. So the fact that the roots should be positive is not a necessary, right? It's not necessary to do that. Alright, so we end up with s minus 2 square root of p. Therefore d is the square root of s minus 2, or absolute value, a square root of absolute value of s minus 2 square root of p. So what is s? S is the coefficient of x divided by minus b over a, minus 4 divided by 1, which is 4. What is p? C over a, 1 over 1, which is 1. So s minus 2p is basically 4 minus 2. S minus 2 square root of p, which is 2. Therefore d is square root of 2, the first choice. Question 44. If x1 and x2 are roots of x squared minus 2 square root of 3x plus 2 equals 0, then what is x1 times square root of x2 plus x2 times square root of x1? Again, this seems to be a symmetric expression. If I exchange the position of x1 and x2, I end up with the same expression. And then let's call it d. And the trick here is that whenever we have a square root, we try to square the whole thing. x1 squared x2 plus x2 squared x1 plus twice the multiplication x1 x2 square root of x1 x2. Now if in the first two terms I factor out x1 x2, I end up with p times s plus 2p square root of p. So p s plus 2 square root of p. Okay, so what is p s here? Minus 2 square root of 3 over 1, which is 2 square root of 3. And what is p here? Is 2 over 1, which is 2, right? So what is our d squared here? P, which is 2 times 2 square root of 3 plus 2 square root of 2, right? 2 square root of 3 plus twice the square root of p, which is 2. And we can factor out 2, so 4 square root of 3 plus square root of 2. And this was d squared, and d has to be positive or negative, we don't know. So square root, the absolute value of d is 2 square root of 2 square root of 2 plus square root of 3. Okay. Now obviously in the choices we only have the positive one, so the fourth choice is the correct one. But d could also be negative depending on whether or not the roots x1 and x2 are positive or negative. Now obviously if x1 or x2 are negative, then the square roots are not defined in the real domain. We go into the complex domain. But we can quickly check. So we know that the sum is positive and the product is positive as well, right? And if we check delta quickly, or delta prime is 3 minus 2, which is positive. So we have two real numbers. They have the same sign, they're either both positive or both negative, and the sum positive, we have two real positive roots, right? Because the sum is positive, the product is positive, and both roots are real. Right, note that sometimes it's not possible to use S and P to find the value of an expression. Again, our main assumption was that the expression that we're trying to write in terms of S and P is a symmetric expression. If it's not symmetric, then, well, it's not possible in general. But we can always directly find the roots and then substitute for them. In this case, we can directly use the quadratic equation itself to find the answer. Solve the following question. Okay, question 45. If a and b are roots of 2x squared minus 8x minus 2 equals 0, then what is a cubed minus 4a squared raised to the third power plus b cubed minus 4b squared raised to the third power? Alright, this is complicated, and this is still a symmetric expression, right? Symmetric in terms of a and b. And a and b are those. So if I set a to b and b to a, the expression remains the same. So I should, in theory, it should be possible for me to write this in terms of S and P. But there is a trick here, and the trick here is that see, I can divide the equation by a factor of 2. It doesn't matter. It doesn't change the roots or anything, right? And then and then I know from that is x squared minus 4x is 1. Okay, therefore x times x minus 4 should be 1. If x is the solution to this quadratic equation, then x times x minus 4 should be 1. So a and b are the solution, therefore a times a minus 4 is 1, and b times b minus 4 is 1. Now look what happens to the expression that we are given. If I factor out a, I end up with a times a minus 4 cubed plus b times b minus 4, right, cubed. But I know that a and b are roots, therefore a times a minus 4 should be 1, and b times b minus 4 should be 1. So we end up with a cubed plus b cubed, and we already know that this is s cubed minus 3sp, right? So what is s and p? S is 4 and p is 1. So s cubed is 64 minus 12. So this is 52, the first choice. See, if we had gone with trying to come up with writing the first expression directly in terms of S and P, we had to deal with A6 plus B6, and we end up with the sixth order terms of S and P, which is very difficult to work with. But we reduced the expression to a cubed plus b cubed, knowing that just by looking at the quadratic equation, we know that a times a minus 4 should be 1, and b times b minus 4 should be 1 as well. That helped us a lot in simplifying the expression. Question 46. What is 2x plus y from equations 4x squared plus 4y squared equals 17 and y minus x equals 3 over 2? Alright, so we know that x squared plus y squared is 17 over 4, and y minus x is 3 over 2. Now this is very clever. So let's assume that x and y are roots of a quadratic equation, okay? If x and y are roots, then we know that the equation could be z squared minus sz plus p equals 0, okay? And then x squared plus y squared is what is it? So it's s squared minus 2p, right? And y minus x, therefore this could be a square root of s squared minus 4p, right? Now if we square these two, we end up with s squared minus 2p is 17 over 4. And if we square the second one, s squared minus 4p is 9 over 4. Excuse me. If we take the subtract these two, we end up with 2p equals 17 over 4 minus 9 over 4, which is 8 over 4, which is 2. Therefore, p is 1. So we immediately find the product, and based on that, we immediately find the sum. 17, basically s squared is 9 over 4 plus 4p, 16, 25 over 4. Therefore, s could be plus minus 5 over 2, right? Again, the problem here is that we don't know whether s is positive or negative, right? But then what we can say here is that we are looking for 2x plus y, right? And we already solved for s and p. We know the sum of the two and the product of the two. Okay? And then the question is 2x plus y is not symmetric, right? It's not symmetric. So we cannot just use s and p to find it. And this, we can write this in terms of x plus x and y. And I assume the best thing to do is just write down the quadratic equation, minus x plus p equals 0, right? We already found s. So s could be plus negative 5 over 2. And 2x plus y, the way we're going to find it is let's assume that z squared minus s could be plus minus 5 over 2 and plus p1 equals 0. Delta here is s squared minus 4p, right? S squared minus 4p is the delta of this equation, and our two solutions are s plus minus square root of s squared minus 4p, and we already know what s squared minus 4p is. Divided by 2, right? These are the roots, and therefore 2x plus y could have two solutions. S plus x. It could have two solutions, which is, so if we assume that s is 5 over 2, s is negative 5 over 2, therefore we end up with the two roots being 5 over 4 plus minus square root of 5 s squared minus 4p, which is 3 over 2, 3 over 2. If s is minus 5 over 2, z1, 2, the two roots are minus 5 over 4 plus minus sorry, this is 3 over 4, 3 over 4, right? So in this case, we end up with 8 over 4, 2, and 2 over 4, 1 over 2, right? These are our two roots, and in this case, we end up minus 2 and minus 1 over 2. So our two roots are either 2 1 over 2 minus 2 minus 1 over 2. The product is always 1, okay? And in this case 2x plus y, it could be x could be 2 or 1 over 2, so this could be 3. This could be 5 plus 1 over 2, which is 10 11 over 2, right? And in this case 2x plus y, and is minus 11 over 2 or minus 3. So we, in the choices, we both have 11 over 2 and 3. So these two choices could be potentially correct. Question 47. What should the value of m be if 1 root of x squared plus mx plus 27 equals 0 is to be a square of the other root? So we have two roots, x1 and x2, and we know that x1 is x2 squared. Alright, this is very interesting. Now again, we don't know what m is, but we immediately know the sum of the two, x1, x2, is minus m, and the product x1 times x2 is 27, right? So we know this. Now, we also know that 1 root, so x2 squared, right? So think about this. x1 squared, or x1 and x2 should satisfy the quadratic equation. So x2 squared plus mx2 plus 27 should be 0, right? But x2 squared, from our assumption or from what the problem is giving us, is x1. So x1 plus mx2 plus 27 should be equal to 0, right? That's very interesting. And therefore, what we end up with is the fact that this relation should also hold. x1 plus mx2 plus 27 should be equal to 0. And then what we can say here is that we don't know what x1 and x2 are, right? But what we do know, we know how to find them, right? x1 and x2 are basically so what is the delta here? The delta is we can use another thing. So x1, so the idea here is that we need to find x1 and x2 in terms of m, okay? So x1 plus mx2 is minus 27, but from the sum we know that x1 plus x2 is minus m. Now if we subtract these two, m minus 1 times x2 is equal to m minus 27. Therefore x2 is m minus 27 divided m minus 1, right? And then what we realize that, okay, what is x1? x1 is minus m minus x2, m minus 27, m minus 1, okay? Which is minus m plus m minus 27 divided by m minus 1, which is minus m minus 1, m squared minus 27, okay? And then x1 times x2 should be equal to 27. So x1 times x2, m minus 27, m minus 1 times m squared minus 27, m minus 1 should be minus 27. And we can solve m. We can solve this equation to find m, right? But again, we can look at the choices that are here. Um, uh, Either it's plus 12, negative 12, plus 12, 11, or 1. Obviously, it's not 1, right? Let's try, for example, 12. So what happens if m is 12? Let me see. So what did we do here? We wrote down the sum of the two roots, x1 plus x2, and was negative m, x1, x2, 27. And then we use the fact that x1 is equal x2 squared, right? But we could do the other things too. So x1 plus x2 is negative m. So x1 is x2 squared plus x2. So I'm substituting for x1 in the sum is negative m. Okay? And the same thing, x2 squared is minus 27 minus m x2. So as we found that x2 is m minus 27 divided by m minus 1. All right? And then we found m1. And I guess instead of solving this, we can solve the equation that x1 is x2 squared. But again, I think the easier thing to do here is to substitute the choices. So let's assume that m is negative 12. Then x2 is minus 39 divided by minus 13. This is 3, right? And x1 is minus m squared, 144, minus 27 divided by minus 13. So we end up with 13 here, 7 here, and then 11, which is 9. So x1 becomes 9, which is x2 squared. Therefore, m should be negative 12. Okay, first choice. We could solve it. It becomes a cubic equation in terms of m, but we could just easily substitute the choices there. Question 48. In equation x squared plus kx plus 1 minus k equals 0. So the coefficient of x squared is 1, the coefficient of x is k, and the coefficient of x to the 0 is 1 minus k. Find k such that one root is 1 unit less than the inverse of the other root. So if x1 and x2 are the roots, we are looking for k such that x2 is 1 over x1 minus 1. Okay? And if we, obviously x1 is not 0. And let's multiply this by x1. So x1, x2 is 1. So x1, x2 is our p, right? So p, and what is s and p? Let's see. S is minus k and p is 1 minus k. Okay? But now we know that 1 minus k, p should be 1 minus x1. Therefore, x1 should be k. So one of the roots, x1, is actually k. So the other root, x2, is 1 over k minus 1, or 1 minus k over k. So now we know the roots, right? And we just use the information from the p product. Therefore, we can put this back into the s. So s is minus k, which is x1 plus x2, k plus 1 minus k over k. So 1 minus k over k is basically, or let's put it the other side. So I bring 1 minus k to other side. So k minus 1 over k should be 2k. 2k squared is k minus 1. And we already know how to solve this equation. Minus k plus 1 equals 0. Delta is 1 minus 8 minus 7. So delta is negative. So there is no value for k. Choice number 4.